It's a great pleasure to, ça fait très plaisir d'introduire notre conférencière au colloquium aujourd'hui, Eva Bayer-Fluckiger, qui va parler, qui va donner le colloquium. She'll speak today on knots, polynomials, and signatures.
Merci beaucoup, Henri. So thank you very much for the invitation to all of you. It's a great pleasure. So last time when I gave a colloquium in this context, so I was actually present in front of a blackboard, so it's a bit different, and but it's also very nice like this. Another difference is that that time I gave a talk on number theory, and this time it's not theory. So why? It's not because I changed completely topics. Actually, so it's about the work on number theory, but I realized that there were applications in knot theory. So that's always cool, you know, when you see that doing research in a certain topic and it has some applications elsewhere. And also, so I chose this topic of knots because there are nice pictures to show. So nicer than maybe number theory. And also, it's easier to present the history, which is much younger. Okay, so there are some pictures of knots, very, very beautiful. And so I would like, as I said, I would like to start by the history of the topic. So it started in the 18th century, which is much more recent than number theory. And usually one says that the beginnings of knot theory in mathematics start with Vandermonde. So in paper, Problème de situation. And so as it was several times done in the time, so he pointed out that there's a sort of geometry that is not a question of measurement, but a question of position. So the manner in which the threads are interlaced, whether something is knotted or not, so that's the crucial thing. So he didn't say much more in this memoir. But then Gauss, who else, so came into the picture. So among many other things, he also worked on knots. Although he didn't actually publish anything, but in his NA class, so in the papers that found after he died, there were three sort of documents. So the first two actually are very short. So very early on, so he was born in 1777, so in 94, it's the first document in the NA class. It's a collection of knots, drawings of knots. And then there's a very short paper, I will show you, in which he defines the linking number of two closed curves. And he mentions geometry situs, so again, the geometry of positions. And then a much longer document, so several parts, which contains a method for the tabulation of knots. So how to make tables of knots. So that is something more technical. And so actually I looked at it a little bit. You can now find all this online, and so it's really like a journal, because here first page he says, so yes, this and this problem, it doesn't seem easy. Then second page, yes, it is easy. So it's a sort of the developing thing. Okay, so now I show you some pictures. So this is the drawings of knots. So some pictures of knots that he reproduced. It is in English, so probably something he copied from a book in English. So no other comment. And then the second document is actually something that is inspired by physics, a problem in physics. But in this paper, it's a half a page only, and he defines what he now call the linking number of two curves. And so he notices that this is, as he would say today, it's a topological notion. And so there is, this is just the first few lines of the paper. So talks about the geometria situs, that Leibniz found this word, geometria situs or analysis situs, and explaining that there's a geometry that is not a geometry of measurements, but of position. And so he said that after 1.5 centuries, we don't know much about it, but certainly introducing the linking number is a progress. Okay, so now no more about Gauss, but Gauss had a student, Listing, who wrote a book for students of topology. And an important thing that he did was to invent the name topology. So this is the first time that the mention of topology, so this word of topology is used. It is a Listing. Okay, so now the next person is Tate, who was a Scottish physicist, and he was very enthusiastic about the study of knots, because he thought that there was a physical motivation that atoms were actually knots, and then molecules would be links, so that several knots interlaced. So that was a theory at the time. And so he was full of energy, and so he thought, okay, so let's just start by classifying all knots, and when we are finished, then we will study physical properties and so on. So it's a full program of research. And he had some very nice hypotheses and sort of conjectures, but he just made statements and didn't prove them. So today we say there are conjectures. And he made tables of knots up to 10 crossings, which is actually quite a lot. So himself, together with some collaborators, they did this rather impressive work. Okay, so this is Tate. And so this is a very modest table of the first knot. So ordered by crossing number. So the first one is the trefoil. Then you have the figure 8 knot. And then there are 2 knots with 5 crossings and so on. So of course it grows a lot. And okay, so one can make these tables as Tate and his collaborators did, because after a while they convinced themselves that, for instance, the trefoil and the figure 8 knot are not the same, and that this knot with 5 crossings cannot be reduced to the figure 8 knot, for instance. But this is completely just by trial and error. So they were not able to prove that, for instance, the trefoil and the figure 8 knot are not the same, because they have no ways of proving anything like that. So this has to wait a little bit later by the start of topology. So I quote Poincaré. So Poincaré didn't work on knots, but he initiated the study of topology, which makes it possible later on for huge development, and also many people who worked on knot theory. So I just quote Alexander and Seifert. There were many others. So they were among the first. And for instance, Alexander, who defined the Alexander polynomial, it was probably the first knot invariant, and that distinguishes between the trefoil and figure 8 knot. So because you find for each of them, find polynomial, and you see that they are not the same. So that shows that the knots are not the same. So now things really started to develop a lot. So Seifert, in particular, proved that every knot bounds a connected oriented surface. So this we call this surface Seifert surface. This was in a paper in 1934 über das Geschlecht von Knoten. So Geschlecht is genus. So the genus of the surface is the genus of the minimal one is genus of the knot. So this was a big progress in knot theory. So here are some pictures of Seifert surfaces, very beautiful. And he also introduced a bilinear form associated to Seifert surface that has the property that a of xy minus a of yx is the intersection form of the surface. So actually, Seifert and almost everybody else in knot theory, so they speak in terms of matrices. So a Cypher matrix is a matrix that represents the Seifert form. And because A minus A transpose is a matrix of the intersection form, so its determinant is equal to 1. So we can suppose that we have a Cypher matrix with non-zero determinant. Now, there is an important theorem of Seifert that characterizes Cypher matrices. These are just the square integral matrices with the property that the determinant of A minus A transpose is equal to 1. So any such matrix can be realized by a knot. So, and later in the talk, we will speak about existence of knots with certain properties. So this can all be proved using this theorem of Seifert, that if we exhibit a Seifert matrix, certain properties, then immediately we get a knot, thanks to this theorem. Okay, so also using Seifert matrices, we can define some not invariants. The first one is the Alexander polynomial. So it has also, there are many possible definitions of the Alexander polynomial. This is one. You take a Seifert matrix and then look at the determinant of AX minus A transpose. So this is a polynomial with integral coefficients, which is called the Alexander polynomial of the knot. It is symmetric, and the value in 1 is the determinant of A minus A transpose, so it has to be equal to 1. Okay, so it's a knot invariant. If two knots are isotopic, then they have the same Alexander polynomial, and because the trefoil and the figure 8 knot have different polynomials, we know that they are not isotopic. Okay, and another invariant that was defined much later in the 60s is the signature. So let's take a Seifert matrix associated knot, and we symmetrize it. Then we have an integral form, a symmetric form, and one can define the signature of the knot as being the signature of this form. And again, one can show that this is a knot invariant. So if two knots are isotopic, then they have the same signature. So now what I would like to talk about is comparing these invariants. So, okay, so when you have some invariants, we want to know which values it can take. So for both of them individually, it is known. So for the signature, it's actually quite easy to show by taking sums of knots. That the signature can be any even number. Okay, the trefoil has signature 2, so and the inverse of the trefoil has signature -2. So you can take any sums of that, and so that's not difficult. Now for the Alexander polynomial, it's a little bit more difficult, but it's also characterized. So any symmetric polynomial with the property that the value of 1 is 1 is the Alexander polynomial for 1. But it's not clear whether one can find knots with prescribed Alexander polynomial and signature simultaneously. And so the idea here is to control this. And as we see, one can define a finite abelian group. So actually, it's an elementary 2 groups, so just a product of groups of order 2, which controls the relationship. Okay, so of course we'll see more precisely how. Okay, so the procedure is to take a symmetric polynomial with delta of 1, so Alexander polynomial, and ask, so what are the signatures that are possible with this polynomial? And so I will not do it in general, because right now I cannot do it in general, but I hope to be able to soon. So there are two hypotheses. One is that the polynomial is monic, and the value of -1 is plus or minus 1. So that is actually a more serious hypothesis. So I have to do more work to get rid of them. I'm sure it's possible, but it's not done yet. The second one is only simplifying hypothesis. So this is something one can do more generally, but it makes results easier to state. To suppose that delta is a product of symmetric irreducible polynomials that are all distinct. Okay, So, but even with this hypothesis, there are already lots of polynomials that fall into this category. And this is a nice family of polynomials that are realized as a polynomial of the UV torus knot. So not serious to say the PQ torus knots, but I like to keep P and Q for prime numbers. so I used other letters, just UV torus knot. So this polynomial, it's a product of cyclotonic polynomials. If U and V are odd integers and prime to each other, then they fall into this category that I consider. Okay, so the torus knot, just to show what they look like. So this is the example of torus knot. A torus knot is a knot that you can draw on a torus. So and U times turning around on the meridian and B times the longitude. So they look very pretty. Okay, so now, so still we have this hypothesis, so delta of -1 is plus -1. And having this hypothesis, we will first derive some necessary conditions for a signature and Alexander for a signature to be realized with this Alexander polynomial. Okay, so recall that S is A plus A transpose. This is the form that we want the signature of. So because I suppose that the determinant of A plus A transpose is plus or minus 1, it is a unimodular form. It is obviously even because it's written like A plus A transpose, so it only takes even values. And it's a very classical result that the signature of an even unimodular form is always an even integer. So we know that the signature is divisible by 8, and this is the first necessary condition. Signature has to be divisible by 8. Okay, second, the necessary condition. So for different nature, so it's concerns the roots of the polynomial. We denote by rho of delta the number of roots that are on the unit circle. Then, and the second necessary condition is that the absolute value of the signature is less than equal to this. So this is perhaps a little bit more difficult to see. So to make it easier, you look at A inverse A transpose. So this is an isometry of the symmetric form as it immediate to check. Now we write the Alexander polynomial as being a determinant of A times determinant of Ix minus T. Determinant of A is 1 by hypothesis. And so we see that this is exactly, delta is exactly the characteristic polynomial of this isometry T. And using that, it's actually quite easy to see that the signature is less than, the absolute value of the signature is less than equal to the number of roots on the unit circle of the characteristic polynomial. Okay, so we have these two necessary conditions. Just a few examples. So this is an example that is of the family that I have told you about. So delta 3, 5. It is just the cyclotomic polynomial of the 15th root of unity. It is written out like this. Okay, so the necessary conditions say that the signature, so I now call the signature M, candidate signature. So it has to be divisible by 8, and the absolute value is less than rho of delta. So rho of delta is cyclotomic, so all the roots are on the unit circle. So this means that it has to be less than equal to 8. So we have only the possibilities -8, 0, and 8. Okay, and another polynomial, this one is of degree 10. It has 2 real roots, and the others are on the unit circle. And again, the signature has to be divisible by 8. And rho of delta is 8. It's less than the degree, but because there are 2 real roots, but we have again the same possibilities. Signature can be -8, 0, or 8. Okay, now having seen the necessary conditions, we come to an obstruction group. Okay, so the idea is the following. So I will show you how to construct group that has the property that if it is 0, then the necessary conditions suffice. So every signature that satisfies these two conditions of being divided by 8 and its absolute value is less than or equal to rho of delta is realizable. Okay, so how to construct this group? So we call I the set of irreducible factors. So they are all symmetric because I suppose that. And we define an equivalence relation. Okay, so first, before giving the definition, a preliminary definition. So we look for an irreducible symmetric polynomial and a prime number p. We ask ourselves whether, what happens when we reduce f modulo p. Okay, so to start with, f is symmetric, but when we reduce modulo p, then it can split into factors that are not symmetric. So, for instance, if I take the polynomial x squared minus x plus 1, reduce modulo 2, it is an irreducible polynomial, so still symmetric. On the other hand, if I reduce it modulo 7, then it splits into two irreducible factors, and they are not symmetric. Okay, but what I look at is actually a set that is determined by two polynomials. So I have f and g again. So of course, in the examples, they will be symmetric polynomials. And look at the set of prime numbers so that f mod p and g mod p have actually a common symmetric irreducible factor. So that is a finite set. That often it's empty, but anyway, it's a finite set because there are only a finite number of p's that there are common factors modulo p of two fixed polynomials. Okay, so this set of prime numbers I will denote by v f g. Okay, now using this, we define an equivalence relation on the set I, which is generated by the elementary equivalence. F and G are elementary equivalent if and only if this set is not empty. And then, so actually what is important for us to understand the situation is the equivalence classes of the factors of the Alexander polynomial. But in order to make it a group, we look at the maps of I in Z mod 2Z and look at the subset of maps that take the same values on f and g if f and g are equivalent. And then we divide out by the constant map, and this is the group. It's called the SHA of delta. It's associated to the polynomial delta. Okay, so what do we have now? So we suppose that the necessary conditions hold. So m is divisible by 8, and its absolute value is less than or equal to delta of the rho of delta, sorry. And if, moreover, the obstruction group is trivial, then there exists a knot with Alexander polynomial delta and signature m. So this is the first result. After that, we will see what happens when delta is not 0. Then there will be a specific element in the group, between the dual of the group, that catches the fact whether or not there is actually a knot with this signature. But first, let's look at the example. So our previous example of the 15th root of unity. So this I have already shown. We have these three possibilities, -8, 0, and 8. This polynomial is irreducible. So for irreducible polynomial, the group is by definition trivial. And so the theorem implies that there exists not with Alexander polynomial delta and signature 8 or 0 or -8. And for the example of the Torus Knot 3, 5, actually the signature 8 is realized, but there are other nodes out there with other signatures. Okay, yes, now before going to the more complete criterion of what happens when the group is non-trivial, I would like to introduce a new notion. So, I mean, it's a notion new for the talk, but it was introduced by Milnor in the 60s, notion of Milnor signatures. That played an important role in the history of knot cobordism. Okay, so for definition of the Milnor signature, it is useful to look at the isometry T that we already defined. So A inverse AT is an isometry of S, and we have seen that delta is actually the characteristic polynomial of T. Now, okay, so V will be the vector space over the real numbers that we obtain by transferring our lattice. For each irreducible symmetric polynomial, so they will be so divisors of delta, they will be of degree 2. Then we look at the P primary subspace of V, and the Milnor signature of the knot at P is the signature of S, the symmetric form S, restricted to this, well, I mean, for us, it will be two-dimensional, right? But in general, it can be, of course, bigger, because we have supposed that the factors are all distinct. And but anyway, so we look at the signature of the symmetric form restricted to the subspace. And the usual signature is the sum of the Milnor signatures. Okay, so new question. With X, again, the Alexander polynomial delta, what Milnor signatures are realized? So it's a more precise question. Okay, so yeah, so we ask the same question, given the necessary conditions, we ask for Milnor signatures. So for this, we have to formalize a little bit more what we mean by Milnor signature. So give a name to the irreducible symmetric factors of delta, so in R of X, so they are the degree 2. And then a Milnor signature will be a map from this set to +2 and -2, because all the factors are distinct, so we have only space of dimension 2, and the signature is either +2 or -2. Then min m of delta is the maps that satisfy that the sum over all P is equal to m, so they correspond to signature m of the symmetric form. Okay, now we fix a tau in the set mil m of delta. And the theorem says that if the group is trivial, then there exists a knot with Alexander polynomial delta and Milnor signature tau. And therefore, of course, if this is taken in mil m of delta, it will have signature m. Okay, so back to our example. So this I have shown you again already, all the necessary conditions. So the m's, the possible m's, there are 3 of them. And okay, now to the Milnor signatures. So the roots of delta are, of course, the 15th roots of unity. And therefore, we will have 4 irreducible polynomials over the real numbers, symmetric, P1, P2, P3, P4, that are all of the shape x minus omega times x minus omega inverse. Where, okay, so these are primitive roots of 15th roots of unity. Okay, so now, what do we have? So mil 8, so that means that the signatures add up to 8. there is only one, because all the values must be equal to +2 if we want to have a sum of 8. It is the same thing for Milnor of -8, because then all the values must be equal to -2. Whereas if we are aiming for signature 0, then there are 6 elements, because there are many more ways of adding up to 0. Okay. And yeah, and so just to conclude, by the theorem, because polynomial is irreducible, hence the group is trivial. So these are all realized. All 6 elements are realized. Okay, now to a more precise result, we suppose that the necessary conditions hold, and we take a Milnor signature. Then one defines a homomorphism that depends on the choice of the Milnor signature. So in the case where this group happens to be non-trivial, we look at element of this dual, which has the property that there exists a knot with Alexander polynomial delta and Milnor signature tau, if and only if this homomorphism is 0. So that is a little bit technical to define the homomorphism. So if you are interested, you look at my paper where it's written down. But this is the result. Okay, so now let's look at some examples. So of this family of polynomials delta UV. Now I will take 2 distinct odd prime numbers. The property that they are, okay, so I have written, yeah, actually it's enough to suppose Q congruent to 3 mod 4. Okay, anyway, and but they are both odd, and we look at U equal to power of P and V equal to Q, and then consider the polynomial delta P E Q. So that will be a product of E cyclotomic polynomials. And actually, it depends, the answer depends on whether or not P is a square or not modulo Q. So it turns out that if P is a square modulo Q, is not a square modulo Q, then the group is trivial. And therefore, the necessary conditions are also sufficient. So there exists a knot with Alexander polynomial delta and signature M, if and only if M is divisible by 8, and the absolute value is less than the degree of delta, because here, I mean, all the roots are on the unit circle. It's just a product of cyclotomic polynomials. On the other hand, if P is a square modulo Q, then the group is not trivial, and working out all the details, one gets that there exists a knot with Alexander polynomial delta and signature M, if and only if, of course, M is divided by 8, but the absolute value is much smaller. So there are some values that are not possible. And of course, if we look at the Milnor signatures, then it's even more precise. So one can tell which Milnor signatures are not possible and which are possible. So a numerical example now. So let's take P equals to 3 and Q equal to 7, E equal to 2. So now this is our delta, the product of 2 cyclotomic polynomials. So polynomial of the 21st roots of unity and the 63rd roots of unity. And here, because 3 is not a square modulo 7, the group turns out to be trivial. And there is a symmetric irreducible common factor of these polynomials modulo modulo 3 actually, because 3 is the, yeah. So the set that I have defined corresponding to polynomials is equal to the prime number 3. It's not empty, so the group is trivial. Therefore, all the signatures that are a priori possible are realized. So all these signatures divided by 8 occur, and all the and for all possible Milnor signatures corresponding to these values, we do have a knot. So I have written down the number of possibilities. So again, in the positive case, so if I want a signature to be 48, then there's only one. And then it increases, so there are more and more choices, possible choices, more and more possible Milnor signatures, and for each of them, the knots exist. Okay, now what happens if we exchange the role of P and Q? So then we look at the polynomial that is a product of the 21st root of unity as before with the 147th root of unity. So it's 3 times 49. And because 7 is a square modulo 3, so we see that actually in this case the group is not trivial, it is of order 2. Because these polynomials don't have any symmetric common factor modulo any prime. Okay, so necessary conditions are like this. So divided by 8, and the absolute value of m is less than or equal to the degree of the polynomial, which is 96. So these are the necessary conditions, but they are this time not sufficient. Because, okay, so now we look at the homomorphisms, and there exists a knot with given with polynomial or polynomial delta and with given Milnor signature tau, if and only if this homomorphism is 0. And this is not always the case. So if I denote by mil delta plus those for which epsilon tau is 0, so then we can count how many there are. Okay, so there aren't any for signature 96. So because actually there is only one possibility, and this one doesn't occur. It doesn't have epsilon tau 0. Now, signature 88 is possible, but a priori, the number of possibilities is 12 times 94. And those that are possible, there are only 12 times 21, so quite a few less possibilities. So there is no knot with the Alexander polynomial delta signature 96, and there exists knots with Alexander polynomial delta signature 88, but not all Milnor signatures occur. So one can, one can count, of course, more generally, which are the possibilities. I didn't write them all down. And so before finishing, I wanted to say a few words about the history of very short history of this topic for me. As I said, so I started out by a question of in number theory. It is a question due to Gross and Macmillan. It's about isometry. So this is how you can say that it's connected to what I have explained. Isometries of given characteristic polynomial of unimodular lattices of given signature. So this is a number theory question, and it is of interest also for automorphism of K-C surfaces. So that was one of the reasons, one of the motivations of this paper of Gross and Macmillan. So actually they asked the question of which are the characteristic polynomials for which there exist even unimodular. I didn't write even. They wanted even lattice, even unimodular lattices of a specified signature. Okay, they in their paper they have shown some results already, and they conjectured what the answer should be for irreducible polynomials. And then recently with Lenny Thalmann, we answered positively their question. So we showed that the conditions they gave for an irreducible polynomial to realize are actually the right ones. But for reducible polynomials, it was already Gross and McMullen knew that their conditions were not sufficient. And actually, so there is a Hasse principle question. And I have a paper on arXiv. It's called Isometries of Lattices and Hasse principle, in which this question is solved by giving an obstruction group of the sort that I have described and a Hasse principle procedure. Okay, so having finished rewriting this, I was it occurred to me that one could use this in knot theory, because I knew that if I suppose that the Cypher Matrix determinant 1, then one can have a signature that can have an isometry that is actually defined over Z of an even lattice, and of course in some cases it's modular, so one can have some applications. But I wasn't sure how interesting this for knot theory. So actually, of course, I knew about the Alexander polynomial. I didn't know much about signatures in knot theory, and so I just typed in Google, and so there were an enormous number of papers on signatures in knot theory. So I thought, it must be interesting. And so I completed my paper by writing down these applications that I just wrote. And yeah, so I would like to mention a paper in which I have learned a lot of things. The paper by Gis and Ranitsky, Signatures in Algebra, Topology and Dynamics. It's a very long survey, and it's very nicely written, and lots of references. So many references I found in this paper, and also they explained about Milnor signature and many other sorts of signatures. Actually, there are many other signatures that are interesting in knot theory, but I didn't want to mention them because it's a bit more technical. And so anyway, what did I have? Yeah, so what I wanted to mention still, that I said before, one would like to have a complete answer. So for any Alexander polynomial, I have supposed that delta is a product of distinct symmetric irreducible polynomial. So this hypothesis is not a problem. So because one can have multiple factors that can be dealt with. It's just more difficult, more complicated to state the results. There are also there can be factors that are not symmetric, but I mean they come in pairs. So products of irreducible factors that are symmetric, so they don't pose any difficulties. On the other hand, it's more difficult to get rid of the hypothesis that the Alexander polynomial, that the Alexander polynomial is monic. In other words, that the Seifert matrices which one works are have determinant 1. So that is more work, and also to have a quadratic form that is not unimodular is more of a problem. So I hope that it will be possible at some point, but not right now. Okay, so thank you very much for attention. Thanks.
Thank you very much, Eva, for your lecture. So I guess I invite the participants to maybe mute themselves if you want to have a round of applause for Eva.
Thank you, thank you.
So are there any questions for? So maybe if you have a question, you should either speak up or maybe Oh, I see maybe some things in the chat. No, okay, so nothing in the chat. Okay, so I was wondering.
Ask a question?
Yeah, oh, sorry. Okay, Octave raises his hand.
I try to raise a hand. So
yes, I have seen actually.
There are a lot of people, so I don't have everyone on my screen.
Yeah, yes, so please.
This is a technique. So did you look at how, so you know, in topology, signatures are very often used in cobordist questions.
Yes, 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 absolutely.
And did you look to similar questions in that context? Maybe.
Actually, it seems, yeah. So Miller signatures were defined in, I mean, the 60s to show that that code cobordist groups were big, right? Okay, so now, yeah. So, but of course, not all problems are resolved yet on cobordism of classical nodes. So this, yeah, I haven't seriously done this, so, but it is definitely, it's a good question. So I think that if I want to do that, I really have to go out of this classical sort of signatures and look at so-called L2 signatures and
Yes.
other representations. So this is, I think it's interesting, and I think there is, so I don't know, but there is some hope that that I could do something in this direction, but I didn't do it yet.
Also, you know, topologists use now a lot of fancy other types of homologies.
Yes.
Like, to study knots, like, I don't know, it's something called Hegardt floor homology, for example.
Right, yeah.
All sorts of other tools.
Yes,
and
yes.
In fact, in all these examples, there is some sort of version of signatures that shows up.
Right, yeah, right,
and,
right.
So I'm just saying that as a topologist, my reaction is that there is a lot of ground to still cover.
You are right. Yes, yes, you're right. I think it's quite promising. So who knows? I mean, I'm not sure, but there is certainly a possibility, because I mean, basically, so there are two things that are being compared. So there's an integral structure that is given by, in this case, by form, and then there is a real structure of all sorts. And to understand how they are interrelated. So this is basically what I'm doing here. So definitely, I hope to be able to do this in other contexts also.
Thanks.
Are there any other questions?
Maybe I can follow Octave in what he mentioned. For torus knots,
yes,
there's especially Covan homology that is very interesting with the nice structure. And while you were talking, I computed an example, one of your example, and you get something naturally out of it that is the Poincaré series of the Covan homology. And if you look at it, it nicely, it writes the Alexander polynomial that you were looking at nicely as a sum of products of cyclotomic polynomial. So a very special sum. So might be that through this avenue, you would have another way of understanding properties of the signature. So you would look at these more sophisticated version of Alexander polynomials, say. That's a way of thinking about it.
Yeah, good idea. Absolutely. Yes.
So there's lots of things that have been done recently on this. Yeah.
Yes.
So I had a question. So you associate to any knot this matrix A and thereby a symmetric bilinear form, or quadratic form with z coefficients, together with an isometry on it. And then you consider the signature, but is it does one get interesting knot invariance by considering the quadratic form itself? maybe over,
the quadratic form certainly is also an invariant. Yes, yes.
But is it useful? Is it? Well, why does one only consider it over the?
Yeah, it is the quadratic form of the knot. It's called. Yes, it is. Yeah, it is an interesting invariant. Yes, definitely.
It would seem like a much finer invariant than just a signature, right? Or is it?
Yes.
That
definitely. Yeah, it is.
And can one ask questions about it? Like, is given such a...
There are so many questions you can ask. Yeah, no, of course. So, but I mean, no, I think it's a very interesting question that you're asking. Okay, so for instance, I mean, in the case of the signature being maximal, right? Which lattices do you get? It looks very, very difficult, but it's very interesting. Yeah. Yeah, absolutely.
So maybe another question which is related to this one. In your result, when you show that there exists, given a certain Alexander polynomial and a certain signature, a certain Milner signature, there exists a knot. Does your result actually produce examples of such knots?
Well, one can, because Seifert tells us that each time you give a Cypher matrix, there is an algorithm to produce a knot. But okay, so I didn't do any computations, but no, I think it would be very interesting. So, for instance, I mean, think of this cyclotomic polynomial of 15th root of unity. So there is a very natural 10 crossings knot, the Torus Knot, but then there are other knots. How many crossings do they have, and what other invariants they have? I don't know, but I would be very curious to know. Yeah.
Yeah.
So hi Parimala, I can see you.
Hi, Eva.
That's been a long time.
Nice to hear you.
Yeah. Yeah. Any question? No.
I don't know if there are any. Virginie, I see you're still recording.
Do you want me to?
Let me just ask for last time, or if there are any further questions or comments.
I think there's a question in the chat.
Oh, okay.
I don't see it.
Oh, okay. I see.
Can you see? Can you read it to me, because I don't see the chat?
I'll read it to you because
yeah,
yes,
please.
okay.
But I don't.
Exactly. So it's a question by Orson Tifanel Mengara, and the question is: are all ciphered forms necessarily realized by knots?
All Seifert forms, yes.
Yeah, so that's
yes, because that's the theorem of Seifert. Yes, in 1934. Yeah, so anytime you give yourself a Seifert form, a Seifert matrix, right? So he gives an algorithm to produce a knot with this Seifert matrix. Yeah, that is very nice, of course. Yeah.
And then there's a follow-up to that question, given the delta, the polynomial and the different shapes, either sigma p or the pair RS, is there always a knot with the Alexander polynomial delta and Milner's signatures corresponding to the different shapes?
What do you mean by shapes?
I don't know. I'm just reading. Maybe I don't know if the person, maybe the person who posed this in chat doesn't have access to, can't speak up.
No, all Alexander polynomials are realized. So any symmetric polynomial with the property that delta of 1 is realized by a knot. And the question of the signature. So this is exactly what we discussed. But shape, I don't know what it means.
Yeah. Yes, I'm not sure if the person who asked this question is still here anyway. So it's anyway.
Yeah. Yeah, it is interesting, but I don't see the chat actually. So this is anyway.
Yeah, you have to. I mean, I clicked on it, and then you.
Yeah, but I have. Of course, I still have my slides. So anyway.
Yeah.
You read it out to me when you see something.
Right. Yes.
Mm-hmm.
Yeah, so are there? So there are no further comments or reactions, I want to thank again Eva for a lovely
Thank you
presentation.
very much. It was really a pleasure. Thank
Gracias.
you.